Our next topic involves the subject of hashing. Now, hashing is a method of cryptography, but it's not really encryption like symmetric or asymmetric is. So there are some differences here, and we'll talk about those. Hashing is basically a method of taking text, and that could be a word, it could be a password, it could be a data file of some sort, and those files or words, the input, if you will, could be any length, any variable length, and describing it as a fixed length string of ciphertext. In other words, a hashing algorithm will look at a piece of text, a document if you will, and basically describe it in terms of metadata and convert this down into a single fixed length digest, message digest. It's like a summary of the document if you will. It's kind of difficult to describe. Now, hashing is a one-way functional model. Unlike encryption, you typically don't reverse it, so you don't decrypt a hash. What a hash is for is basically to ensure integrity and allow you to compare two hashes together to see if they match. Now, hashing is used in several different things in cryptography. You can hash a password for storage and transmission. You can also use it to confirm that a piece of data has not changed, and that would give you integrity of the information. And hashing is also used extensively in digital signatures. It's difficult to explain, but hashing basically is a method of deriving a value based upon an input document or text. Now, hashes are also called message digests. You may see that term. They provide for integrity data, and they can encrypt in a way, but it's not really called encryption. Basically, you can convert a piece of text or a string into a hash, and that hash is typically unreadable by humans, and in most cases unreadable by machines to the extent that it can't be reversed. Now, these values, these message digests that are produced from running the hashing algorithm on data are always unique to a message or input, and they're not duplicated by another message. If this occurs, this is called a collision, and that's where weaknesses can come into play. MD5, for example, has been proven to have collisions in it, meaning that you could produce two separate hashes that are identical from two separate non-identical pieces of text or input strings. Now, what we don't do is we don't decrypt hashes. So what do we do with them? Well, we could take a hash produced by running an algorithm on a password, for example, and then we might take that hash and send it across the network. Now, a hash is also stored in a database, say Active Directory, for example. So when you log in, you put in your password, the password is hashed, the hash value is sent across the network, that hash value is compared to a hash value that's stored in Active Directory, for example, and if they match, if they're identical, then we know that the user input the right password. The Active Directory side of the house doesn't know what the password is, it just knows what hash is produced when a hashing algorithm was ran against the password. So that way you ensure integrity of the passwords themselves. Now, there are several hashing algorithms that we'll talk about. There's RIPE-MD, 128-bit, and a lot of these have been compromised. Now, when I say compromised, they've been proven to have collisions, or they've been proven that they can be in some way reversed. And the most common ones that we see these days are MD5 and SHA, or some variation of SHA. But even those have been compromised or theoretically compromised in some cases. In fact, the whole family of SHA-2 has technically been theoretically compromised, although there are no practical known hacks against those algorithms. Recently, NIST, who basically selects the national standard for the United States for algorithms, recently decided upon KATSAC as the replacement hashing algorithm for the national standard, and we're going to call it SHA-3 formally. And as you can see on the charts, there are variable bit lengths for these hashing algorithms. MD5 has a 128-bit hash, SHA-1 160-bit, and they progressively get higher. And of course, theoretically, the higher the number, the more secure the algorithm. So we've got all these hashing algorithms here, and you should memorize at least the MD5 and the SHAs for the exam and know what bit size you have for them. Now, in the next session, we're going to actually look at a couple of tools that will run hashes on passwords or words or documents so you can actually see what this process looks like, and that will probably help you get a better idea of how this works when you see it in action.